everyone, this is Babitha, working as Assistant Professor in the Department of Electronics and Communication Engineering at Institute of Aeronautical Engineering. In this session, I am going to discuss the problems related to diode resistance. So before going to the problems on diode, first of all, we have to know the operation of the diode when we are providing the forward bias as well as reverse bias to the diode. Generally, if we join both the P type of semiconductor material as well as N type of semiconductor material to make the PN junction diode. So as soon as if we add or join these P and N type of materials, the junction will be formed between both the materials. So once the PN junction is formed means the majority charge carriers which are present in the P type of material, those are holes, and the majority charge carriers which are present in the N type of semiconductor material, those are electrons. Those are trying to diffuse or move towards the opposite directions. That is nothing but holes will diffuse towards the N type of material and electrons are trying to diffuse towards the P type of material. So because of this diffusion process, there is the formation of depletion layer, formation of the depletion layer near the junction in both the P type of material as well as in the N type of material. So once one electron is coming from N type of material and joining with the hole, it leaves its negative charge and it becomes a positive immobile ion. So each and every electron which is leaving from the N type of material becomes the positive immobile ion. And similarly, this particular electron is accepting by this hole is having actually positive charge. So once it is accepting the electron means it becomes the negative immobile ion. So because of this diffusion process between P and N type of material, more number of negative immobile ions are formed in the P region and more number of positive immobile ions are formed in the N type of region. But this particular region we can call it as the depletion region. So once the depletion region is forming in the PN junction diode means there is no movement of charge carriers between both the materials now. So in order to make the flow of charge carriers and in order to flow the current in the device, we have to provide the bias to this particular device. So here we can provide both the biases, forward bias as well as reverse bias to the PN junction diode. So if you wanted to provide the forward bias to the PN junction diode, we have to connect the positive terminal of the battery to the P type of material and the negative terminal of the battery to the N type of material. So here the holes of P type of material are repelling by this positive terminal and electrons are repelling from this negative terminal of the battery. That is nothing but these particular charge carriers are moving in this direction and these electrons are also moving in this direction. Both the electrons and holes are moving towards the depletion region. So because of this movement or force, the charge carriers are diffused into the depletion region. Okay, charge carriers are diffused into the depletion region. So those are recombining here. So if you still increase the forward voltage, the depletion region will disappear here. So once the depletion region is disappearing means there is a flow of current in the device. So generally here the movement of electrons are in this direction. So the forward current which is flowing in the device from left to right. Because of that reason only diode we are representing with forward arrow symbol with anode and cathode terminals. This is in the case when you apply the forward bias. Similarly, if we apply the reverse bias to the PN junction diode, in that case we will connect negative terminal to the P type of material and positive terminal to the N type of material. So in this case, the holes are trying to attract towards the negative terminal, and similarly the electrons are also attracting towards the positive terminal of the battery. So because of these, the charge carriers, the majority charge carriers which are present in the P type of material as well as N type of material are coming away from the junction. So the depletion region width still more it is increasing in this particular reverse bias condition. So once the depletion region width is increasing means the movement of charge carriers is decreasing. It is almost zero. So that's why there is no current flowing here. That is nothing but the forward current is zero in the reverse bias condition. But the minority charge carriers which are present in the P type of material as well as N type of material are trying to diffuse towards the depletion region. So because of that movement of minority charge carriers, we will get very small current or leakage current, that is the reverse saturation current in the case of diode. So these two type of currents we can expect in the case of PN junction diode when we are operating in the forward bias condition as well as in the reverse bias condition. So now we will see how much current we are getting in the forward condition as well as in the reverse condition of the diode. Further, I am considering the diode current equation. That is, so this diode equation gives the expression for the current through the diode as a function of the voltage. That is nothing but how much amount of voltage we are applying, that corresponding current we can get from the diode. So according to ideal diode law, the diode current equation is expressed as I equal to I naught into e power v by eta vt minus 1. So this is the current which is flowing in the diode. So here where I naught is nothing but the reverse saturation current in amperes. Reverse saturation current we are getting in the reverse bias condition of the diode. I have already explained. In the reverse bias condition, we will not get any current due to the majority carriers. We will get the current due to only minority carriers. That current we are calling it as reverse saturation current. We are representing here it as I naught. Okay, it is in mostly we will get in microamperes. It is very less value. And this value also again depends upon which type of diode we are utilizing here. Germanium diode or silicon diode. So if it is germanium diode, we will get it as some microamperes. And if we use the silicon diode, we will get it as some nanoamperes range. And V is nothing but the applied voltage that may be in the forward bias condition or in the reverse bias condition. Suppose if we wanted to take in the forward bias condition, in that case, V is nothing but Vf. And if we take in the reverse bias condition, V is nothing but Vr. Generally it is negative minus Vr in the reverse condition. And eta is nothing but the equalization factor in the case of junction, that is indicates equalization factor is nothing but it will indicates the quality of the device. Quality of the device is nothing but how much depletion region width is very less. The doping level is very high means the purity of the device will be high. So this purity of the device we are indicating with the parameter, that is eta, and this value is 1 for germanium diode and 2 for silicon diode. And Vt is nothing but voltage equivalent of temperature in ohms. There is nothing but temperature in terms of voltage we are representing here. So in order to calculate this Vt value, that is equal to K into T. K into T. So here K is nothing but the Boltzmann's constant and the value of that one is 8.622 into 10 power minus 5 electron volts per degrees Kelvin. So this is the standard value we need to remember to solve the problems. And T is nothing but temperature in degrees Kelvin. And here we need to calculate the Vt value. So to calculate the Vt value, we have the relation that is Vt equal to T by 11,600. So how we got this particular relation is nothing but generally at room temperature we will take it as 27 degrees Celsius. Room temperature we are taking here it as 27 degrees Celsius. So this 273 is the standard temperature here. So in order to calculate the Vt value, always T we have to take it as sum of the given room temperature value plus standard temperature. So here room temperature value is 27 degrees and the standard temperature value is 273. So that is equal to 300 degrees Kelvin. So at 300 degrees Kelvin, the value of Vt if we calculate, we will get it as 26 milliohms. So generally to calculate Vt value for any temperature, this 26 millivolts for 27 degrees Celsius, suppose we may take it as 24, 26 or 25, anything. So for that particular different temperatures, we have to use it as T by 11,600. That is T by 1 by K. That is nothing but T divided by 1 by K value is 8.62 into 10 power minus 5. So if we simplify this, we will get it as T by 11,600 and T is nothing but sum of the room temperature plus standard temperature. Okay, so this is the diode current equation and this particular diode current equation is applicable for both the forward bias as well as reverse bias condition. The only difference here it is, in the case of forward bias, you have to take V as Vf. In the reverse bias condition, you have to take V as Vr here in the diode current equation. And next, in the diode, we are going to calculate the diode current equation problems as well as we are going to calculate the static resistance as well as dynamic resistance of the diode. So here dynamic resistance is nothing but the reciprocal of slope of VI characteristics of the diode. That is nothing but from the slope of VI characteristics we will calculate the resistance of the diode. So that we are writing here it as R equal to 1 by slope of graph. That is 1 divided by variation of the current with respect to the variation of the applied voltage. So now how we can calculate this particular 1 by di by dv. So to calculate this value, first of all we have to calculate di by dv value. So to calculate di by dv, first we require the diode current equation, that is I equal to I naught into e power v by eta vt minus 1. So this equation, take it as 1, differentiate this equation with respect to v. So if we differentiate this equation with respect to v means we will get it as I naught into e power v by eta vt into 1 by eta vt, and differentiation of 1 is nothing but 0. So di by dv we got it as I naught e power v by eta vt divided by eta vt, but here we require R equal to 1 by di by dv, so we have to take the reciprocal of this particular equation, that is eta vt by I naught e power v by eta vt. So this is the formula for the dynamic resistance, and we can also write it as, but from the current equation we can also write the dynamic resistance as I equal to, if we expand the current equation, that is I equal to I naught into e power v by eta vt minus 1. If we expand this, we will get this particular equation. In this, if we take I naught to the left side, we will get it as I naught e power v by eta vt equal to I plus I naught. So here R is nothing but eta vt by I naught plus I. So this is also the formula for dynamic resistance. So in the problem, depends upon the given parameters, we can utilize either this one or this one. These two are belongs to the dynamic resistance formulas of the diode. So how we can get from the characteristics means, so this is the forward voltage and the forward current if we represent on the graph. So we will get the curve in this way. This indicates the cut-in voltage. So after cut-in voltage, there is a sudden rise of current here. So in order to calculate this, I am taking 2 points on the curve. Any 2 points we can consider. I'm considering 2 points on the forward curve. So this variation will give the variation of the forward current, or del VF or del V, and the corresponding change in the current we are representing with del IR, del IF. So this one will give here the resistance, it is V by I, that is del V by del I. So from this curve we can take two values here. Suppose this may be a 0.3 value and this may be the 0.4 value, and here it is 2 milliamps or 4 milliamps. So the difference of these two currents as well as the difference of these two voltages will give the dynamic resistance value. So from the curve also directly we can calculate, but formula here to calculate the dynamic resistance is this one as well as this one. And one more parameter we can calculate, here it is VF and IF. I am considering the VI characteristics of the PN junction diode. So again I am taking the forward curve. To find the static resistance, you have to take only single point on the curve. So that corresponding voltage as well as current will give the static resistance, capital R, that is V by I. So in the dynamic, while calculating the dynamic resistance, we are taking the variation of the voltage with respect to the variation of the current. But in the case of static resistance, we are taking only single point. At that point, how much voltage we are applying and how much current we are expecting for that particular applied voltage. So now we will see the problems related to the diode current equation and the static and dynamic resistance of the diode. So here the given problem is find the value of DC resistance and AC resistance of a germanium junction diode at 25 degrees Celsius with reverse saturation current I0 equal to 25 microamperes and at an applied voltage of 0.2 volts across the diode. So here the given values are, we need to calculate DC as well as AC resistance, that is static resistance. DC resistance is nothing but the static resistance and AC resistance is nothing but the dynamic resistance. So we need to calculate these two values, and at 25 degrees Celsius, so the given temperature it has 25 degrees Celsius and the reverse saturation current is I0 equal to 25 into 10 power minus 6 amperes, microamperes, and applied voltage V equal to 0.2 volts. So the given temperature I0 as well as V values, we have to calculate the static and dynamic resistances here. So here we know the dynamic resistance formula. That is I plus I0 divided by eta Vt, or else we can also use eta Vt by I plus I0, or eta Vt by I0 into e power v by eta v. We can use this formula or this formula here. So here to find the dynamic resistance, first of all we have to calculate the current in the circuit or current in the given question. So to calculate current, we have the formula I equal to I naught into e power v by eta vt minus 1. So here I naught value is given, that is 25 microamperes, that is 25 into 10 power minus 6. E power V is nothing but the applied voltage, that is 0.2 volts, divided by, which is a germanium diode. So for the germanium diode, eta value is 1. And here to calculate this, first we require the Vt value. And Vt formula is T by 11,600. So the given temperature here it is 25 degrees Celsius. So 25 plus 273 divided by 11,600. So this one we will get it as 39.59 volts. So that Vt value we have to substitute here. Minus 1. So this one will get the current value as, so if we solve this we will get the current value here. And next to find the static resistance, or that is nothing but V by I. V value is 0.2 already given. So what is the value we are getting here? I, we need to substitute to get the R value here, that is the static resistance value. And similarly, to find the dynamic resistance RD, we can take it as eta Vt by I plus I. So eta value is 1 here. Vt is 39.59 ohms divided by, what is the current we are getting from here, plus 25 into 10 power minus 6. So if we solve this, we will get it as 791.8 K. And this is 8 K. We will get it as 8 K here. So in this way we need to calculate the static resistance as well as dynamic resistance for the given problem. And the next problem is the voltage across the silicon diode at room temperature of 300 degrees Kelvin. So the given temperature value is 300 degrees Kelvin here, is 0.7 ohms. That is nothing but applied voltage is 0.7 ohms. When 2 milliamps current flows through it, it is nothing but the forward current is 3 milliamps. If the voltage increases to 0.75 volts, that is nothing but I am taking it as V new voltage, 0.75 volts. Evaluate the diode current. So at 0.7 volts, we got the current as 3 milliamps. If I increase the voltage from 0.7 to 0.75, how much current we are getting? We need to calculate. And they have given Vt as 26 millivolts. So no need to calculate the Vt value directly. I mentioned in the problem 26 millivolts. Just we need to calculate current, new current, how much we are getting. So in order to calculate the new current, how much we are getting from this problem, first of all we require the reverse saturation current. So to calculate the reverse saturation current, again I am taking the current equation, that is I equal to I naught into e power v by eta vt minus 1. So here I value is 3 milliamps, that is 3 into 10 power minus 3. I naught we don't know. E power v given value is 0.7 volts. And it is silicon diode. So eta value is 2. And Vt value is 26 millivolts. So 26 into 10 power minus 3 minus 1. So if we simplify this, we will get the reverse saturation current as 2.84 into 10 power minus 9 amperes. So this is the reverse current. Then when the voltage is changing from 0.7 to 0.75, how much current we need to calculate? So for that, I'm taking I equal to I naught into e power V new value we need to substitute here. V new by eta Vt minus 1. That is nothing but I equal to I naught value is 2.84 into 10 power minus 9 into e power 0.75 divided by 2 into 26 into 10 power minus 3. So if we simplify this, we'll get the new current as 5.231 milliamperes. That is nothing but previously the current was 3 milliamperes when voltage is equal to 0.7. Now voltage is changing to 0.75. Current is changed to 5.2. That is nothing but if 0.5 variation in the forward voltage, there is a almost 2 milliamps variations in the forward current. And we're coming to the next problem. It is given problem is the reverse saturation current of a silicon PN junction diode at an operating temperature of, so the given temperature is 27 degrees Celsius, is 50 nanoamperes. So the reverse saturation current I naught equal to 50 nanoamperes. Estimate the dynamic forward and reverse resistances of the diode. That is nothing but RD resistance in the forward bias condition as well as RD resistance in the reverse bias condition. How much we need to calculate. And while calculating the forward bias dynamic resistance, we have to take voltage as 0.8 volts given in the problem. And to calculate the dynamic resistance in the reverse bias condition, we have to take the reverse voltage as minus 0.4 volts. So we need to find the dynamic resistance in the forward bias condition as well as in the reverse bias condition. So to find that dynamic resistance, we have the formula that is eta Vt by I plus I naught. So here we require Vt value as well as current I value to find the dynamic resistance. So first I am calculating the Vt value by using T by 11,600 formula. So T is given as 27 degrees plus the standard temperature is 273 degrees Celsius divided by 11,600. So if we simplify this, we will get it as 0.02586 volts. So this is the voltage equivalent of the temperature. So next we need to calculate the current. I equal to I naught into e power V by eta Vt minus 1. So here I naught is 50 nanoamperes. So 50 into 10 power minus 9 e power V value is 0.8 volts divided by, and it is the silicon diode. So eta value is 2 and Vt we got it as 0.02586 minus 1. So if we simplify this one, we'll get it as 234.81 into 10 power minus 9. And next we need to calculate the R resistance in the forward bias condition. Okay. That is I plus I naught by eta Vt. or else we can also use the equation eta Vt by I naught into e power V by eta Vt. So if we choose this one, the forward resistance in the forward bias condition is 2 into 0.02586 divided by 50 into 10 power minus 9 e power V value is 0.8 divided by 2 into 0.02586. And to find it in the reverse bias condition, we will get it as 2 into 0.02586, that is Vt value, divided by 50 into 10 power minus 1, that is I naught value, into e power. Here V value is negative, we need to take, that is minus 0.4 volts given in the problem, minus 0.4 divided by 2 into Vt value is 0.02586. So if we simplify these two, we will get it as dynamic resistance in the forward bias as well as dynamic resistance in the reverse bias condition. And next problem is determine the values of forward current, that is I, in the case of PN junction diode with I naught, that is reverse saturation current is 10 microamperes, and VF, that is forward voltage, is 0.8 volts. At T, temperature is given as 300 degrees Kelvin, and assume it as silicon diode. So we need to find the how much forward current which is flowing in the circuit by using these parameters. So here the formula for finding the forward current is I equal to I naught into e power V by eta Vt minus 1. It is nothing but here at 300 degrees Kelvin, the Vt, we will get it as 26 millivolts. In the previous problem also we have derived, or else if you want to calculate again, the formula is T by 11,600, that is 300 divided by 11,600, we will get it as 26 millivolts. So I naught is 10 microamperes, so 10 into 10 power minus 6 into e power Vf is 0.8 volts, and it is silicon diode, so eta value is 2 into Vt is 26 into 10 power minus 3 minus 1. So if we simplify this, we will get it as the forward current of the diode. And the next problem is an ideal germanium PN junction diode has a reverse saturation current, that is given I naught is 30 microamperes at a temperature of, that is capital T, equal to 125 degrees Celsius. Find the dynamic resistance R for V equal to 0.2 volts in the forward condition as well as V equal to minus 0.2 volts in the reverse bias condition. That is nothing but indirectly they are asking for forward and reverse dynamic resistances. So to calculate that forward and reverse dynamic resistances, we are having the formula R equal to eta Vt by I plus I naught, or eta Vt by I naught e power V by eta Vt. So here we require the value of I here, remaining all are there. So to calculate the dynamic resistance, first of all we need to calculate the voltage equivalent of the temperature Vt as well as current which is flowing in the diode. So first I am calculating the Vt value. Vt equal to T by 11,600. So the given temperature value is 125. So 125 plus 273 degrees Celsius divided by 11,600. If we simplify this, we will get the VT value. So after finding the VT, we need to calculate the current in the diode. That is I equal to I naught into e power V by eta VT minus 1. That is nothing but I naught value given it as 30 microamperes. That is 30 into 10 power minus 6. E power V value is 0.2 ohms divided by, it is the germanium diode. So eta value is 1. And VT, how much we are getting here, we have to substitute here. And if we simplify this, we will get the current of the diode. And after finding the diode current, next we have to find the dynamic resistance RD in the forward bias condition by using eta VT by I plus I naught. So if we use this particular expression, we cannot utilize the forward voltage as well as reverse voltage. So that's why we're using I naught into e power V by eta VT. So here eta value is 1 is given in the problem. VT we have calculated here, divided by I naught is 30 microamperes. E power V given it as 0.2 volts in the forward direction. Eta is 1 and V. If we simplify this, we will get the forward dynamic resistance. And similarly, to calculate the dynamic resistance in the reverse bias condition, that is eta VT by I naught e power VR by eta VT. That is eta value is 1 because of germanium diode. VT divided by I naught is 30 into 10 power minus 6 e power reverse voltage given it as minus 0.2 divided by 1 into VT. So if we simplify this, we will get the dynamic resistance in the reverse bias condition. So the next problem is determine the dynamic forward and reverse resistance of the PN junction silicon diode. So here it is silicon diode. So for this eta value is 2. When the applied voltage is 0.25 volts at T equal to 300 degrees Kelvin with reverse saturation current is 2 microamperes. So same, we need to calculate the dynamic resistance in the forward bias condition as well as in the reverse bias condition. It is nothing but to find that first we need to calculate VT again, that is T divided by 11,600, that is 300 divided by 11,600. 300 Kelvin is the standard temperature. If it is given it as 300 Kelvin means we should not add the standard temperature to this. If it is given in the range of 20s or 100s only, we need to add the standard temperature. It is 300 Kelvin means it's already in the standard form. So 300 by 11,600 means again we will be getting here it as 26 millivolts. So next we need to find the current. This VT and current are required to find the dynamic resistance. That is I naught into e power V by eta VT minus 1. That is I naught is 2 microamperes. That is 2 into 10 power minus 6 into e power V value is 0.25 divided by, it is the silicon diode. So eta value is 2 into VT is 26 millivolts minus 1. If we simplify this, we will get the current. So after finding the current, we have to find the dynamic resistance in the forward bias condition by using eta VT by I naught e power V by eta VT. That is 2 into 26 into 10 power minus 3 divided by I naught is 2 microamperes. That is 2 into 10 power minus 6 e power V's forward voltage is 0.25 divided by eta is 2. Again 26 into 10 power minus 3. If we simplify, we will get the forward dynamic resistance. And similarly, to find the dynamic resistance in the reverse bias condition, the equation is modified as eta Vt by I naught e power minus V by eta Vt. It is nothing but 2 into 26 into 10 power minus 3 divided by 2 into 10 power minus 6 into e power minus 0.25 divided by 2 into 26 into 10 power minus 3. So if we simplify this, we will get the dynamic resistance in the reverse bias condition. And the next problem is determine the dynamic forward and reverse resistances of PN junction silicon diode. Here the applied voltage is 0.25 volts and the temperature is 300 degrees Kelvin. And the reverse saturation current I naught is equal to 2 microamperes. So here we need to find the parameters RD in forward bias condition, RD in the reverse bias condition. As like in the previous problem, we need to find Vt as well as I to calculate the dynamic resistance in the forward bias as well as in the reverse bias conditions. So Vt equal to T by 11,600. So for 300 degrees Kelvin, we will be getting it as 26 millivolts. And the current equation is I naught into e power V by eta Vt minus. That is nothing but 2 into 10 power minus 6 into e power 0.25 divided by, it is silicon diode, so eta value is 2 into 26 into 10 power minus 3 minus 1. If we simplify this, we will get the current value. So after finding the current value, to find the dynamic resistance in the forward bias condition, that is eta Vt by I naught e power V by eta Vt. And similarly, to find the dynamic resistance in the reverse bias condition, that is eta Vt by I naught e power minus V divided by eta Vt. So in this case, eta value is 2, Vt is 26 millivolts, so 26 into 10 power minus 3, I naught is 2 microamperes, that is 2 into 10 power minus 6, e power V given it as 0.25 ohms divided by 2 into 26 into 10 power minus 3. If we simplify this, we will get the forward dynamic resistance. And similarly, if we substitute the values of this one, that is eta is 2, Vt is 26 into 10 power minus 3, and I naught is 2 microamperes, that is 2 into 10 power minus 6, e power V is minus 0.25 ohms here, divided by 2 into, that is eta into Vt, 26 into 10 power minus 3. So if we simplify this, we will get the dynamic resistance in the case of given problem. So in this way, we can able to find diode current as well as static resistance as well as dynamic resistance of the diode by using the diode current equation as well as dynamic resistance formula of the diode. So in order to find all these values, we have to analyze the PN junction diode in the forward bias condition as well as in the reverse bias condition. From that analysis, we can get the current equation. From the current equation, we can able to find the dynamic resistance as well as static resistance of the diode. Or else from the characteristics, from the VI characteristics of the diode also we can calculate the static and dynamic resistances directly. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.